I'm Soumyendu Sarkar from Hewlett-Packard Enterprise, and our paper is on reinforcement learning platform for adversarial black box attacks with custom distortion filters. Now, the success of machine learning models relies on their robustness against naturally occurring distortions. The minimum distortion of efficiently generated adversarial samples can be a practical measure of robustness if we limit the distortions to the types encountered in the use cases. Now, in real world, the visibility into the model is not always available, and there are IP concerns for white box testing. In black box attack, there is partial visibility to no visibility to the model. The proposed approach requires access only to the classification probability distribution of the model's output. Now, this is one of our initial work where we were just using the Gaussian noise as distortion. And as you can see, over the period of time, the Gaussian noise is progressively getting added. And this is causing the beer glass to get misclassified as a gas pump. Now, we use reinforcement learning, adversarial black box attack agent that identifies sensitive regions in the input image and progressively adds Gaussian noise or other type of distortions as we are going to introduce later to those patches until the model misclassifies. Now, for each step, the RL agent uses a novel dual action of adding distortions and removing previously added distortions, which have become less effective for misclassification. Now, this novel method is equivalent to a deep tree search with limited computation. Unlike the game of chess, here you can take back a move later on without any penalty. That's the big advantage. Now, the RLab beats the state-of-the-art black box L2 attacks in terms of average number of queries by a wide margin with a low failure rate and with very competitive L2. The figure below, we will show how it compares to the popular soda attacks. Now here, as you can see, the agent progressively adds distortions. It goes to the image classification model, where the reward is, as we are going to discuss, how the ground truth probability is changing, and then it evaluates and it takes further actions till misclassification happens. Now, the difference between the modified data and the original data is a measure of robustness, L2, LP, the different measures are there. Now, if you look at the reinforcement learning agent, here what is happening is the states, which are the sensitivity of adding or removing distortions, they are helping the RL agent to take action, and the RL agent adds distortion to certain block patches, and it removes some previously introduced distortion from certain patches. It goes to the classifier, and the classifier determines the change in the probability dilution of the ground truth, normalized by the added L2 distance, the delta of the L2 distance, and that becomes the measure of the goodness of the action or reward. Now, this happens still. The ground truth is less than the top K for the untargeted attacks, or this can also act for the targeted attacks when it is compared with the probability of the targeted class. And this continues. Now, on misclassification, there is an additional step of cleanup, which further removes the distortion without flipping the classification back, creating the adversarial sample. Now, this shows a little bit of details as how we estimate the sensitivity map of adding distortions and removing distortions, which features in the states, and based on that, the actions are taken to add or remove distortions, and one of the hyperparameter is the number of blocks, maximum number of blocks to which distortion can be added, which we try to limit. And we keep the number of blocks from which the distortion is removed one less, so that the agent converges fast enough. However, when the distortion is removed from previous moves, on certain steps, L2 can actually go down a little bit. Now, on this shows uh, more details. And here, the most important thing to note is it can add various distortion types. If you compare with the soda, if you see with the square attack, there's a bad patch. There are color bleeds with the patch attack, the bad patches. As compared to that, if you look at our lab, this preserves the true nature of the image. Here we are just using Gaussian noise, and you can see the amount of distortion is pretty minimal. Now, now we come to the meat of the paper, where what we're proposing is you can bring in a mix of distortions. In the spirit of the bring your own booze, it is bring your own distortion. And this allows the user to plug in one or more of their own distortion filters for adversarial attacks which is realistic to their use cases. And then our lab adds a minimum amount of distortion with a mix of these distortion types to input images to cause the models to misclassify. And these are some examples of the Gaussian noise. The blur we are going to explain later is hard to figure out, and the dead pixels and differences in illumination. Now this shows like how the distortion are added, and you can see red is the Gaussian noise, blue is the Gaussian blur, pink is the dead pixel, and white are the brightness. And with the original image, if we add certain distortions, then it becomes misclassified. It's somewhat hard to decipher, but once you know the map, it's a little bit easier. So the same thing here is for the bulbul, and this shows like dynamically how we are adding these different distortion types to the bulbul, and then progressively the classification score of J is going up till at some point of time J over X bulbul, we are keeping the L2 pretty minimal. Now, this will show how the Gaussian noise affect the images. If you see the comparison, it becomes easier. This is for Gaussian blur, which was hard to find, but now you can figure out, where the Gaussian blur is happening. There's very tiny blurs here. And again, this is on the head of the bulbul and the beak of the bulbul. Now here, this is very perceptive. No one taught it to hit right in the bullseye of the sea anemone, and that's where the blur is causing distortion to make it misclassify for the jellyfish. Now this is for the dead pixels. These are some of the comparisons with the state-of-the-art with ImageNet, dataset, and ResNet. As you can see, our lab, the average number of queries is very low, and the L2 is very low also, and very competitive. So is the L infinity, and with 100% misclassification. This shows from the same for C410. And this is the ablation study of the patch size. As the patch size goes down, our lab has more efficiency in reducing the number of queries, lowering the L2 score, etc. Now, if you see among some of these state-of-the-art attacks, here we're comparing VGG16, Inception V3, and RegNet 50. Overall, our lab is better than these other state-of-the-art attacks. CG attack is a little bit better than VG16, but overall our lab outperforms. Now, this is a comparison with the state-of-art for targeted attacks. And here also you can see that our lab significantly does better. Now, this is for the different filter types: Gaussian noise, brightness, Gaussian blur, and dead pixels. You see the average query is the lowest for Gaussian noise, and so is the L2. But the mix is always a better option. Now, this is again evaluation of the different the hyperparameters of the different filters which are most effective marked in bold. Now, we can use our lab to retrain the models with adversarial samples to increase the robustness. And this shows, like, when they're trained by Simba, Square Deck, and RLab, how they're performing against these different, like, attack matrix, and RLab has the best results. We can also use it for visual explanation, like for localization mask and the heat map. And this again, like, our method stands out in that respect. We can extend our lab for one-dimensional ECGs for similar, and for more than one dimension for videos where we use the hierarchy of the spatial agent and temporal agent. We can see that our method had least amount of distortion to cause the misclassifications. Now, in conclusion, our lab outperforms the state-of-the-art insert matrix. Now, it can use multiple custom distortion types relevant to real-life use cases, and it can be extended for one-dimensional like ECG and videos. It can be used to enhance robustness and visual explanation. This shows, like, all the certain dimensions that can be handled by our lab with explainability and increased robustness. Thank you. And this is from thanks to our team in machine learning research group at Hewlett Packard Enterprise.